Or this computer. Entendido. Okay. So yeah, thanks again for this second session. We are here again with part of the stochastic modeling course, and I will go a little bit deeper on the theory that we just saw last week, which is this chemical organization theory. So I'm gonna use a little bit of slides and of articles and a little bit of whiteboard to speak about to speak deeper about the theory. And in 1 hour, we will see how far I can get. And if there is interest, we can continue later. So I will recap a little bit with the reaction networks and what chemical organization theory is about. So the basic, you remember we got a set of species and a set of reactions. Here we got 5 reactions in this example. I guess, if you don't follow anything, if there's something you don't follow, just stop me and I will re-explain. So L will refer to light, S1 will refer to some sort of species that can self-replicate in the presence of light. And then S2 is a sort of about to die form of S1, because S2 can die while S1 can become S2. So it's like young, old. I will say S1, maybe it's a sort of reproductive state of a species, while S2 is a non-reproductive state, but something that can get younger if it has enough light. So it can come back to the reproductive state. And if it doesn't come back, it might die. So this is a sort of just any form of something that can be self-maintained in a community or in a group way. If there is enough light, then S1 will replicate, that will turn into S2. Some S2 will die out, but the whole system will kind of survive, will self-maintain. So it's a small example of an autopoietic system. But of course, as I explained before, this can be turned much more complex. And so the interesting thing here to recap conceptually, to make a conceptual recap, is that this system, we can actually build a dynamical system, which can be described, for example, by this differential equation, which is the simple application of mass action kinetics. That, as I explained before, it means that everything can interact with everything, and everything is homogeneously distributed in a space. So chances for interaction are proportional to the concentrations. And the speed of the reaction is given by this constant, K1, K2, K3. So we build the differential equations. This is a simple exercise that anybody can do at home. And we get these differential equations, which cannot be solved analytically, at least not easily. And so it's normally the kind of system you have to simulate. So then we can choose any initial state and then choose any kinetic parameters, and we can apply simulations. So the idea now, yes, Gabriel, one question here. It's isn't here. Yeah. I have to mirror the screen. Sorry, my students here are not seeing my screen, so I have to mirror. No, I just have to mirror. Keep changes, and now. Yeah. Okay, so small recap for them. So this is the reaction network, 5 reactions, 3 species, and 3 species, 5 reactions. And if we build the differential equations, we will get this system. The differential equation for light, for S1 and for S2. So the interesting thing is to change the view from the perspective of trying to solve the differential system to think of what processes can happen to this system and what processes are interesting. By process, I mean what collections of reactions, what pathways can occur. So I just give an example here to show that different parameters for the differential equation, if we simulate it, we will get completely different stuff. Here we get some sort of oscillatory behavior that kind of converges to a fixed point where the three species are present, light, S1 and S2. Here we got a slightly different initial condition that lead us to the big presence of S1 and a very small presence of L, R, and S2, maybe even decay. I don't know exactly if the number is 0 or not here. And the third gives us an oscillatory regime that it looks like it's going to converge to something where S1 and S2 decay. They tend to peak and then decay and peak and decay. So we don't know exactly what's going to happen, but we see that the dynamical behavior of this already very simple system can be quite different at the qualitative level. So instead of focusing, that's the idea of chemical organization theory, instead of focusing on the parametric conditions that make changes of these different qualitative behaviors, we will look at the landscape of qualitative behaviors before thinking of the kinetic parameters. That's the trick. So if we look at the mass action kinetics, recall, for example, reaction, we'll show this reaction, S1, reaction 2. S1 plus L gives 2S1, and the first reaction is nothing gives us L, so inflow of L, and the second one is S1 plus L gives us 2S1. So if we look at the vector here, this is the flux vector. This is the process over time. This is what happens over time. We got a kinetic parameter K1 explaining how much inflow do we have per time unit, and the amount of times that the second reaction will happen that is going to be equal to K2 S1 times L, because the mass action kinetics tells us if at a given time we got the reaction 2 will happen proportional to the concentration of S1, the concentration of L, and the kinetic parameter K2. So this is actually the amount of times or the rate at which the reaction 2 is going to happen over time. The same we can do for every possible reaction given a kinetic law. This is the mass action kinetic law. If we have a Michaelis-Menten or we have a decision-making based law, kinetic law, we will get other numbers. But everything will always be seen as a vector. So this is why we can rewrite the differential equation in an linear algebraic form with a matrix, stoichiometric matrix, times the flux vector, process vector, which we call it process vector because we want to think of processes rather than fluxes as in chemistry. So having this view in mind, we will focus on the structure that these vectors can have. That's the interesting thing. And as I explained here in the article, we can choose very complex kinetic laws here. We can oscillatory light, for example, if we got day and night, we can modulate the inflow of light with a periodic function. We can use for this interaction, the one that we see here, we can have a mass action, but here we can have some sort of this type of kinetics represents that there is a saturation rate. This is the Michaelis-Menten, the saturated kinetics, and so on. So we can even mix kinetics depending on the properties of the reactions we are modeling. And that makes the differential equations extremely complicated, very hard to solve analytically, etc., etc. That's why we prefer to move to a different domain of thought, which is the phase space. That's why I want to show this picture first, that we got the concentration space on the one hand, and on the other hand, we get the process space. So as I showed before, the flux vector, the process, will be determined by the kinetic parameters and the concentrations in the system. So we can tell that every point in the concentration space will map directly to a point in the process space. And actually, we have a fixed point when the process space maps back to the same point in the concentration space, because what it does is that all the reactions happen, but the concentrations remain the same, because what is spent in one side is created on another side of the reaction network. So this is an abstract picture of a fixed point in the concentrations process interplay space. We can have dynamics that are expansive. That means that we start from the deep blue color. We start from a certain region of the phase space. This is more like related to the Monte Carlo simulations that I receive a few questions about. So if we start from a certain region of the phase space, the dynamics will map to a region of the process space, which in turn might map to a larger region of the phase space. So we will have an expansive dynamics in the kinetic in the phase space. But we also can have a contractive dynamics. That means that when we start from a very large region of the phase space, our kinetics will lead us back to a smaller region of the phase space. And we can have some sort of complex stability, like a limit cycle or a periodic orbit and so on, where we get points and points that map to different places, but the regions remain fixed somehow. So if this idea is clear, if this interplay is clear, we understand, we can have the idea that we don't need to look at the specific kinetics to know how expansive or contractive these things are. It's more interesting to look at what the arrows do, regardless of what dynamics is ruling the happenings of these different arrows. So this idea, I might feel that is not easy to digest. So if there is any doubt at this point, I will be glad to discuss. But if we get the fixed point part, it's actually quite good. Is this clear? This plot, this figure? Yeah. Yeah. Okay. Cool. Then I can continue. So now that if this is clear, then the idea of COT, back to just a simple motivation, the idea is to understand how the structure of the network allows to know information at this level. Because if we have an ecological system that is very hard to solve, for example, we might know information at this level. But this group of species can function in a stable way. And if we have a perturbation, maybe instead of having we will have an expansion. So this is the kind of questions that we will start asking, rather than if I have a very large system and I put all these parameters, where is it going to lead me after 10,000 iterations? That is not anymore. The question is more like trying to build up a theory of how can we harness information from the structure of the network to understand how these arrows might work. Okay. So now this opens up lots of things. And this is why I will now do a little bit of theory on the whiteboard to clarify these notions. Okay, so then I have to start the whiteboard. I hope this okay, let's aim for thick. Yeah, okay. Back to this. Okay, so I will try to keep this this equation here. Hey, no, this pen. This equation is this S is the stoichiometric matrix, V is the flux vector. Is this clear to the audience? Do you remember what I mean by this, or shall I make a small example to clarify?
Small example.
Okay, I will make a small example. A goes to B and B goes to A. This is a simple network So this vector, you can look to this as a vector -1, 1, and to this as 1, -1. Because here we got A, here we got A, and here we got B for both. So 1A is produced, 1B is consumed, or 1A is consumed, where B is produced. So then if we take this as a matrix, we'll get -1, 1, 1, -1. If this we multiply it by a vector xy, this is the process vector, which is here. This is the stoichiometric matrix. Okay, we will get -x plus y, comma, x minus y, right? This is equal to that. And this is the production of the system given the process V. So you get a structure which defines S, you get a process that tells you how many reactions you're gonna have happening at a given time span, and that will give you a production. In this case, x plus y, or minus x plus y, x minus y is actually something like Z minus Z. So because the one is the negative of the other, then the only way in which this thing can be sustainable is with Z equals to 0, which implies x equals to y, which implies that both reactions must happen at the same rate, so the system is self-maintaining. If the reactions don't happen at the same rate, then something is going to be lost and something is going to be overproduced. Something is going to be, let's say, exploiting the other. If A is producing more B than B is producing A, then B is kind of accumulating at the expense of A. And that's the idea, that we look at this in this way at the dynamics. So back to the notion, SV equals to, we call it XV, which is the change in the concentration driven by the happening of B. Okay, and this is where we can start introducing notions. For example, if SV is larger or equal than 0 and V is larger than 0 for all instances, so we can call it VI is larger than 0 for all I. What are we saying here? This is important. I mean, this is fundamental to understand, to interpret. What does this mean? This means that the production of all the species, so the vector xv, which is equal to that, right, is larger or equal than 0. That means no species is reducing its concentration. No species is reducing its concentration. That's what that means. And this means all reactions are happening because all of them have strictly larger than 0 value. So no reaction has rate 0, and all species are not reducing because they can be larger or equal than 0. So these two conditions define self-maintenance. Okay, so this is a first notion, first concept to understand. Okay, any question here? No? Okay. So now that if you have questions, can go back, no problem. So once we understand that we can play with the conditions that we impose to the production, and to the process, we can define a sort of landscape of possibilities. Actually, for example, what if I define this? What will that mean?
Some of your reactions may not be proceeding.
Sorry, say it again.
Some of the reactions might not have any velocity to them.
And this is what you say before. You just said this, but what will this mean?
Yeah, but
Nothing is lost.
you're still gaining mass in those.
The production of species is strictly positive. So we don't have, like as we had before, that we have larger or equal. Now we have strictly larger.
Can you go back once? Like I need the before information to follow there.
Yeah.
Okay. Okay.
So this condition, the condition SV larger or equal than 0, means that species are either growing in their concentration or maintaining their concentration. Those that have equal will be maintaining, and those that have larger will be producing. Because as explained in this right part, when we have the reaction network, we define the stoichiometric matrix, and the process vector here defines the reactions that will happen. Those reactions will define a production. And then that production can be negative, positive, or 0 for each species. There is no other option, actually, either negative, 0, or positive. If it's negative, it means that the species is going down. Its concentration is going down. It's reducing. It's a species that is going, like, dying out. We might still have some, but it's going down in the derivative. If it's 0, it means it's maintaining, and if it's positive, it means it is growing. So what we look for instead of doing simulations is to look at what processes do what things to the system. And from that, build a mathematical theory that allows us to understand better what can possibly happen, not necessarily doing simulations, but looking at the structure of possible processes that can operate in the system. And then we need to introduce some properties. One of these properties is self-maintenance, which is described just here. So no species are reducing their concentration, and all reactions are happening. We force the system to operate in its full. A different condition will be this one, which I'm imposing that not necessarily all species, not necessarily all reactions are happening, because I allow the process vector to be equal to 0 for some coordinates. If I say V larger or equal than 0, that means it can be that some reactions have rate equals to 0. But we are also asking that the production of a species is strictly positive. So this could happen, for example, in a system where we have, for example, empty set goes to A goes to B, and B goes to empty set. For example, if I have this system and I allow this to happen 2 times, this 1 time, and this 0 time, then how much am I going to have? I'm going to have 2 A's, right? By this first reaction, I will apply it 2 times, so I will get 2 A's, but one of those A's will be used up to produce 1 B. and this third reaction happens no times. So we will have in the end 1, 1. After the happening of this process, we will get 1A and 1B in our pocket. Do you see? In this case, we are having a concentration larger than 0, a production larger than 0 for both species, but we are not operating all the reactions. Is it clear?
Yeah,
Yes.
but what would be the case in which you have an empty cell producing A?
Inflow.
Oh, good. Sounds good. It was
Yeah.
like production. Okay.
That's the empty set means like out of the system.
Good.
Means, and so when B goes to empty set, it means that B leaves the system or dies out. So it becomes something that cannot be used up anymore somehow, either leaving the system or disappearing, degrading in a form that cannot be reactive anymore to anything else. It's like an accumulation of this doesn't participate in the dynamics anymore. So when it goes in the left side, it means this is coming out of something that is out of our model. Right?
Great. Perfect.
Okay.
Thank you.
Yeah. No, this is good. So these are the type of conditions that we need to introduce. So as I mentioned, we got the self-maintenance and we got the overproduction. And actually, if we want to take SV and we take a specific coordinate, I will use like a Python or kind of programming notation. SVI is the production of species SI in M, right? So we got lots of species. So this I will make a small s to differentiate from the stoichiometric SI. So if we think of this, we can have that SI is smaller than 0, SI is equal to 0, sorry, or SI is larger than 0. For any process vector that we define, we don't have nothing but these 3 options. That's all we can have. This means underproduction. This means self-maintenance. And this means overproduction. Clearly, underproduction, it means if it's sustained for too long, if underproduction is sustained for too long, we will have that the species is going to be depleted at some point. It's going to die out. So this is dangerous. We see that, I don't know, bees are reducing their population over time. They are underproducing. So we see, okay, this is dangerous. So some species are not dying out, so this is okay. And some species are overproducing, which is from a short-term perspective, it's okay, but in the long run, it can have like problematic impacts. But this is okay as well, in the sense that it's not dying out. So now, okay, is it clear? At the level of looking at just this moment, these definitions, when we don't think of a specific dynamics, what's going to happen in the future, but we are looking just at how the network can be operated. This is our perspective to see where locally the dynamic is going to go. So now, if this is clear, then it will be good to introduce a little bit more interesting properties to a reaction network. Back to the idea that organizations, you remember, well, probably organizations defined in the previous class or session, they are closed, means nothing new can be produced, and self-maintaining, there exists a process vector such that SV is larger or equal than 0 and V is strictly larger than 0, then if this happens, then the reaction network is an organization. And if it is an organization, it means then it's a candidate to be stable. Then it will depend on the dynamic conditions. It will depend on many things to be stable or not. But everything that is stable will have these features. So this is not a way to find the stable states, but it's a way to discard what cannot be stable. Okay?
And why,
Mhm.
Matt?
Yeah.
Why must the V has to be larger than 0 instead of larger or equal to 0?
Because it's a sort of epistemological condition. It means that everything that can happen must happen at some rate.
Okay.
So back to the case, A goes to B, B goes to A, and let's say B goes to empty set. Let's say we have this system. This system, if I do not allow this reaction to happen, this third reaction to happen, the system is self-maintaining, because I just operate the first and the second reaction at the same rates, and then the production of both will be 0. Then this condition will be fulfilled. The productivity condition will be fulfilled. But the third reaction is not going to be happening. Now, if you allow the third reaction to happen, then the system is not self-maintaining. You see what I mean?
Yeah, but then I'm still confused because then if you don't allow the third reaction to happen, that means you are in V larger or equal to 0.
Yeah. So if I operate the process vector, this reaction is going to happen one time, and this reaction is going to happen one time.
And this one 0.
Then both the production XV is going to be equal to 0, 0, right? When V is equal to 1, 1. Right?
Yeah.
So then the system here, it self-maintains. But
It's positive.
It's equal to 0. Both reactions are going to be 1, 1. The real flux vector that we need to consider is 1, 1, 0, the real process vector, because the third reaction is not happening. So if we restrict the system to only have these two reactions that I will mark in red, this first system is self-maintaining. The extended system that I look in blue is not self-maintaining.
Right. Got it.
Mm-hmm.
Perfect.
So when we introduce these two conditions, we can define what are the candidates to be stable. And actually, if we look at the whole, let's say I have a reaction network with 3 species, A, B, C, okay? And some reactions are 1 to R7, let's say something, just to give an example. Then we can look at all the subsets of this system, empty set, A, B, C, A, B, A, C, B, C, and A, B, C. These are all the subsets, and we can mark, let's say in green, those that are organizations. For example, these 3. So what we know is that any possible dynamics of this system, the stable states, the steady states in the long run will not be those that are not marked in green. So you can only find stable states within the green boxes. And if you look then at the phase space of this, let's say A, B, C, then what we know is that the fixed points or the stable state will be either on this axis, which means A is present, or at this plane, let's say in yellow, the plane AC, or at the full volume, which means like in points that are outside the plane AB, outside the plane BC, outside the line B, and outside the line C. So the subspaces of the phase space where you can find fixed points will be those that I just marked in yellow. Okay, is that clear?
Yeah.
Yeah. Okay, and so we don't know exactly which point it's going to be the one that the system will be converging to, because we don't even know actually if it's going to be a fixed point or is it going to be a limit cycle, what kind of trajectory in that subspace of the phase space we will find to be the stable. But we know but what we know is that in the long run, the system will only be possibly having those structures. And actually, we know as well the kind of processes that will be happening, because not every process is self-maintaining. That's the thing that I want to stress very importantly. Back to the example, A goes to B, B goes to A. We know that the flux, the process vector, if we got that the stoichiometric matrix is -1, 1, 1, -1, and I multiply this by a flux vector V, with V, as I said, we call it X and Y, right? V equals to X and Y. And then we have that the result, the XV, is going to be equal to X minus X plus Y, comma, X minus Y. So now what this is showing is that if we look at the process space, X, Y, the only processes that self-maintain the system are those in the diagonal. So we make an interesting dimensional reduction between what can possibly happen and what can actually happen in a sustainable way. Because, for example, all these red points here are possible operations of the system, but only those in red over the blue line are going to self-maintain the system. So we know that if a system with two species described by this remains stable, we know that the process will have to be this way. So that's why I was showing before the process space. This is again the process space. And this other is the concentrations space. So there is an interesting interplay between the concentration space and the process space. And now I will, hello, yeah.
All good from here?
Okay. So I hope this is not getting too confusing. So now I want to show a few notions that are really interesting to explain this. The first is that an organization can be decomposed according to the type of productions that they do in a given operation. So if I have an organization, I'm going to call it X. Let me show you with a little example that I have. For example, let's say I got this inflow, something that comes from the inflow that interacts with something else. to produce something here, which in turn produces this back. And this interacts with something else here that produces this back. So we can call this A, X, Y, W, Z. So the reaction network will be empty set gives, I would call it A plus Y gives X, X gives Y, and A plus W gives Z, and A plus and Z alone gives W. Okay, think of this system. If we think of this system, we can notice that although the full reaction network is connected, so everything is connected through lines, so everything is interacting, we can notice that if we have enough of A, and we have some Pac-Man here eating all X, we will notice that the perturbation of having something eating X is only going to affect to this part of the network. Because this is, although A is spent in this process, this is not going to alter what is happening on the other side of the reaction network. Because the process, the way in which X and Y are connected to W and Z are through a species that is not in risk, because it's overproducible here. We got enough, we can have enough A coming from the inflow, and if that happens, then these two things can be decomposed. So depending on how, and this is the deep idea, is that depending on how the network is operating, we might be able to decompose the dynamics of the network so that perturbations will only have limited impacts, but that depends on how the network is operating. If the network is not operating in a way where A is overproduced, as in this case that we have the inflow, but maybe we can have outflow as well. And if we have that outflow larger than the inflow or equivalent, then we cannot ensure that this decomposition will work. So this is the work we did. So we have a network, and in words, we got a reaction, an organization can operate in ways in which we can decompose its productive structure into independent parts. Meaning perturbations will have limited impact. So there is a theory for this, and I think it's going to take me too long to explain the theory that this isn't in articles. So instead, I will show a little bit of a diagram of a Jupyter notebook that we have to describe this. So now I go here, I'll compartir, share screen. Okay. This one, Pedro? We can look at the decomposition here. Oh, yeah. Okay. So I'm not sure if, okay. So we got here an example that represents a farm. Let me show you the farm example. No, can you read that, or is it too small?
It would be great to have it a little larger.
Yeah. So view. So how can I make this bigger?
Perfect.
Yeah. So this is actually one of the examples we have used to describe a little farm. We got inflow of water. And actually, I think I have it here. Main open file. Yeah, this is better. Because we have also a graphic tool to visualize reaction networks, but we also have Jupyter notebooks to prepare the, yeah, okay. So these are the reactions here. You can see the reactions. Inflow of water, actually, yeah, inflow of water, farmer plus infrastructure plus money gives farmer plus 2 infrastructure. Dung gives fertilizer and worms. Chicken plus grass plus infrastructure plus worms gives chicken plus eggs plus fertilizer plus infrastructure, and reactions of the kind. So we just explain like in a sort of narrative how a farm operates. So what dung makes, how chickens become, how chickens produce eggs, how eggs produce chickens, how water is used to grow grass, how can we convert the create milk out of the cow, how can we make money out of the milk, how can we make money out of the grain, out of the straw, and how can we use the money to produce more infrastructure, and also having like decaying of infrastructure, because if we use it too much, it's going to be destroyed over time. So we can make a sort of model of that. And if we build, sorry?
How many state variables are there in total?
How many what?
State variables, like all these variables. What is the total number of variables in this whole process?
Yeah, the total number of species here is 14, and the total number of reactions is 17.
Okay.
So this is a relatively untractable model, I guess, for differential equations and so on. We can still run simulations, but to understand that the structure of it is quite complicated. But if we look at the chemical, at the organizations, actually, of this system, we only find this is the problem, that this tool is under construction. So when I click here, it doesn't show me only the structure that I'm looking. It's showing me the full network. This is a problem of the tool. But I know how to fix this. Just have to rerun the code, and then it's going to show the right thing. This is a part of the in construction tool. It's and also every time we use it, it looks for updates, so it takes a little moment. It's interesting to do software development, actually. There's so many variables. Okay, so the smallest organization possible, it's only water. We have nothing but water. Then the next one has cows, dung, farmer, fertilizer, blah, blah, blah. So this is the next organization. And then the next biggest one, the bigger one that it comes, it has also eggs and chicken, but it doesn't have grain yet, I think. Yeah, so we got the grainless farm, the chickenless farm, and the full farm. And this is the full farm in operation. So we can describe this. It's a very small, simple structure. It's a linear structure. There are no variants here to the sides. It can only be this or that or that. Is a sort of chain of growth. And what Pedro here did is that, okay, here we got the full farm. This is the code. This is not the tool anymore. This is our code. And what we can study with this is the decomposition. There are many ways to decompose the network because there are many ways in which this can be operated, but these are two examples. So in this first example, we can see the green species are those that are overproduced. The green in the diagram are those that are overproduced, and then the yellow ones are those that are only self-maintained, together with the purple one, which is independent of the others. It has a different color. It's part of a different group. As I showed before that we had two groups, here we can have two groups as well. This is, one is of size 1 and the other is of size almost the rest. But there is another decomposition, which is when the network operates in a different way with a different process, in which the two groups that decompose the network are actually quite different. They are both or more or less the same size. So here we got the purple group has 3 species, and the green and the other green group has, there are 3 groups. The overproduced species are this one here, and then there is another darker group of so these are the overproduced, and this is the, sorry, yeah. So here we got another decomposition where the two groups, the two separated groups, have relatively the same size. In the first case, the decomposition shows only one big group and infrastructure as the two groups, as the two decomposed groups. And in the second case, we got that the two groups are decomposed, the two groups are more or less the same size. What am I trying to say here is that if we allow the system to be operated in a way in which can be decomposed into many modules, then perturbations are going to impact only the modules to which the perturbation is connected to. And the other modules might not suffer, at least directly, from the perturbation. The perturbation will last much longer to arrive to this other group, which is independent. And it will depend on the dynamics, but generally the propagation of the perturbation goes first to the group which is sensitive to the perturbation, but that sensitivity is linked to the way in which the network is operating. And that is the, it's a very, I hope this makes sense to you, but it's a very illuminating fact to understand how resilience work, because there are no, that's the call here, is that there are no resilient structures per se. What is resilient is the structure in a specific operation. This is what we show. This is in an article in the journal Complexity. So if you want to check it out, and I think I'm reaching my time here. So I just want to show maybe a little bit of how the propagation goes out, because we were studying as well the way in which how a propagation will, how a perturbation will propagate through the network. We make as an example the worst possible perturbation here, which is eliminating the water from the system, because we are studying at the moment how the species that are inflow, how the inflow, if we cut the inflow from a system, how it's going to propagate its impact. So using the methods that I tried to explain in this little time, we made the following. We have the network in operation, and then we see that once we eliminate water from it, first thing is that cows become non-reactive. In our system, cows cannot die. We work in a time scale where cows don't die. But once water is not available, then cows become not available. And that immediately shuts down a set of reactions. And then we don't have any dung anymore, which in turn has that we don't have grass any long later, and then we don't have worms later, and so on and so forth. So we can study how the perturbation propagates through the network. And with this, we can start studying what perturbations will reach what parts of the network and how long it's going to take. And also we can study the resilience of the network by playing with these perturbations, maybe doing simulations as we have done also in this other article that I was planning to show, but there is not enough time. So I guess this with this I can finish because it's time to finish. And what we have here is a dynamics of propagation of perturbations. We can incorporate the idea of resilience by studying different ways in which the network can be perturbed, and study the impact of those perturbations, considering the way in which the network is operating. The way the network is operating, as I explained before, is a process vector. So we can study not the dynamics of it, but the structural propagation of perturbations. Is that maybe clear?
At least the intuition.
Yeah, because it's quite technical. I'm sorry, but I don't know how to explain this in shorter time. We were discussing with Pedro. It is, and I didn't even explain like 20% of the theory. So it's a linear theory for the dynamics. So we need to be kind of acquainted with this SV, X plus larger than zero, smaller. So all the notions can be introduced. So maybe, okay, so questions, or maybe we can think of maybe an example to work for you to illustrate how the questions you study look in this theory, maybe?
I just want to know that is the structure you're talking about, does it have any relationship with the sign directed graphs?
Has what? Sorry.
Like the structure you have constructed through reactions, and does it have any resemblance with the sign directed graphs, like the graphs we construct for the networks using the community metric?
You mean, are you, sorry, just to rephrase your question, are you asking whether these reaction networks are, how do they relate to the networks you build? Typically in network models, food webs and stuff like that?
Are you familiar? Each person have a different name for this, like sign directed graphs. It's like if you have worked a little bit with Rodrigo Ramos, you might have seen. So those like with the Bacher and others, like that then derives to loop analysis. Like when you have, like for example, you can represent a food chain in which you have so like an arrow has 2 points. One, if it's negative, you put it like as a circle. If it's positive, you put it as an arrow. Okay, that is sign direct graphs. So I already made the platform for you to speak about whatever was the question. So what is the question?
I just want to know, is it similar to the sign directed graphs? Like in that case, if one species is benefiting the other, there is a link and then given by an arrow.
No, so, I understand the question now. Thanks. Is that we are hearing you through the projector, so the sound is kind of not the best. And the answer is yes, it is related, but it's not the same, because the plus and minus, or the arrow and circle that you put to the arrow, depends on how the network is operating. So what the generality, let's say, idea here is that two species can interact in multiple ways. The idea that something is always positive to something else and always negative to something else is the idea that we try to move forward from in this model. So of course we can build an analogous system, assuming that this interaction is positive to this and is negative to that, the fact that this is the fact that a species is present, then it's going to be negative for the other and it's going to be positive for the other. This is going to be just one reaction. Actually, it's like, for example, in the case of, I'm going to write here. So if we got S plus A goes to 2A, so that means that actually this is the vector here, the process explaining this reaction is going to be -1, 1, because S is damaged and A is benefited. So I can just denote this, or maybe A plus B, just to make it A plus B goes to A. So A is gaining 1 and B is losing 1. You see? So we can represent this same idea. So this is the sign directed graph. It's a sort of it's like the basic way in which we can represent interactions. But what if you have something like, let's say, maybe they can also maybe this is not going to make sense directly from a purely ecological, I mean traditional ecological perspective. But what if they become something that then interacts with something else and then it produces 2C? So what if the two things together will make a compound that later on benefits both? And then C becomes back A plus B. I'm just creating a mechanism here. So depending if D is present, this might be, they might be benefited by being together. When D is not present, maybe A only is going to win. You see what I mean? So this idea that sorry, yeah?
When C is present.
Yeah.
When C is present.
Mm-hmm.
Yeah,
I'm gonna make it too simple, just to because I was maybe complicating too much the structure. Let's make it like this. So even like this. So when D or call it C, simple. When C is not present, this reaction cannot happen. When C is not present, this reaction cannot happen. So the only reaction that can happen is this one. A plus B goes to 2A. That means that A is benefiting from B. But when C is present, both A and B become benefited, and C is actually not even changing. So C is just catalyzing the cooperation between A and B, which when A is not present, A and B will, A is going to be the predator of B. So this duality is what I think that cannot be easily represented in the sign directed graphs, because this is contextual. In the context of C, A and B can cooperate. In the different context, they will not. And actually, A is going to eat B out. So that's why we extend the framework to reaction networks. And that's why we think that, or we propose that what is interesting here is to look at the interaction mechanisms seen as reaction pathways to describe collective groups that can operate in a self-maintaining way. And all the rest, what I was showing is like the mathematical theory of how to formalize that, and a little bit of code to show how can we plot that and so on and so forth. But yeah. So will that reply to your question, Taru?
Is it like what I understood is it right to say that in a sign directed representation, you can show the pairwise interaction, but the way you have tried to construct the network, you can move from pairwise to higher order kind of interaction?
Yeah.
Is it
Yeah. That's one of the benefits. But beyond that, that's the thing that I have I think it's beyond just higher order interactions. Interactions are already not purely represented by arrows. Interactions can be represented by sequences of arrows, by mechanisms. So in this
Yes.
case, we will say, okay, there is a, for example, let me go further and say that this creates, for example, C plus A plus B plus X, a new resource, and then X plus A can go to A, and X plus B can go to 2B. So, okay, X plus A plus B, X plus A, B, A plus B. So just to say something different, when A and B, when in the context of C, they will start producing something which is X, but then they will compete for this X. Okay, so 2A plus B and 2A plus 2B. So they will compete for it. Or I don't know if this will be called competition, but they will both together with C, they will produce this X, and then only one of them will get it each time. So this can be thought as a symbiosis, because both can be benefited, but also can be a competition, because X is now the resource that will be used up either to grow A or to grow B. Both will grow eventually, depending on the dynamics, but eventually not. Eventually, just A is going to take all of this. If the kinetic rate of this is very big and this is very small, then this reaction will happen much faster than the other. And then actually A is going to be benefiting out of B. So what I mean is that we take out the idea that interactions are so ontological. Interactions are not there in the world. They kind of happen, or we believe they happen because we see things, but what happened is just mechanisms or processes. So it's a little bit philosophical, this point. I don't know if that philosophical digression will make sense, but that's the intuition.
That does sense, actually, especially in our lab, in which we really care about mechanisms. We don't like net effects like that are defined by the observer. We usually model mechanisms and try to see what is the outcome of those mechanisms in terms of net effects between species. So this is great. This gives even more power to the analysis.
Yeah, it will be nice to model some of the mechanisms you have, put them together in a reaction network, and see if maybe some self-maintaining groups appear in a non-expected way. Because when networks are too complicated, we used to meet, as it happened to me in the last talk, that one of the people in the audience found a box that I should have put it there, and I just skipped it because I didn't check enough and see, okay, this can be self-maintaining too. So that would be something maybe interesting to do.
So it's just given that you asked for one example, I have immediately in my mind that we've been trying to think about is the effect of algae, in particular, let's say kelp, even in the Chilean coast. Like we're working in this project with California, Chile, and South Africa, in which we want to model better primary productivity in the system, and how climate change is going to affect the system, species invasions, etc. And one of the key issues we're having is not including non-trophic interactions in the food webs. Yeah. So the food web is a ecological network, 106 species more or less, and we've been trying to incorporate all the multiplicity of mechanisms that macroalgae have in there, in particular in terms of habitat provisioning, which is a non-trophic interactions that is really hard to model in the framework we have.
Yeah.
Because it's catastrophic interactions and with food web allometry, blah, blah, blah. So it might be a good example, good study system to start trying to apply this. Even not necessarily an entire network because it's 106 species, but maybe a smaller system that is closer to what is happening with the mussel beds and how like the mussels are being promoted in terms of their recruitment by the algae, and but then they're also eat the algae, but then like there are all these different processes that happen with the algae that are many. So you never kind of like, it's really hard with the methods we have right now to actually get them all.
Yeah.
I
No,
think
I think that this will be the best, the good candidate, because the idea actually of this language is that you can just simply list all the mechanisms. They don't
Right.
interfere with each other. You can put them all together, and then the tool will tell you, okay, if we assume that all the mechanisms have to be in place, meaning the V larger strictly to 0, then this is what can happen. If we allow some of the mechanisms to be absent, then this is what happened. And as I was mentioning before, we can look at the process space and see the different regions, meaning activating or deactivating certain mechanisms, or activating or deactivating certain species, and see what can remain stable in those conditions without running the dynamics.
And how about adaptive? How about adaptation, evolutionary dynamics? It's also a mechanism, right? So you can just put it in there, right?
Evolutionary dynamics will in principle mean that, I mean, the only way in which evolution can happen in this framework, so far we could discuss it further, but the way I see is that new species can come in, so mutations that trigger reactions that were not able to happen before.
Doesn't need to be like even species, I imagine. It can be just like, I'm thinking of rapid evolution. I'm thinking of quick adaptation, even just plasticity. So
yeah, I know, but what I mean is species, I don't mean ecological species. I mean species in the model. I mean dots in the graph.
Right. So for example, like I'm thinking of climate change. So climate change is affecting the coast of Chile, to say something. And there is one particular phenotype of the mussel that has like a better shelf for like sustaining the increasing temperature than another shelf.
Yeah.
So then you can model that, right? Like, okay, we are increasing temperature. If we're increasing temperature, we will probably produce more of this shelf because they do better in higher temperatures than this other one.
Yeah. Yeah, this can be modeled. Yeah, I mean, you have, let's say, shell 1 plus light, then we'll get just, and that's it, they die out. And then shell 2 plus light, you'll get shell 2. So this will mean that the mussel 1 dies out with light. This means that the mussel 2 doesn't die. This is an extremely simplistic version of what you're saying. It could be made more sophisticated as well.
Yeah.
So, but that's the idea, that we can describe mechanisms in coarse-grained ways or in more sophisticated ways, depending if you want to say, okay, and we can also describe it at the level of the kinetic rates. We say for shell 1, this reaction happens at a constant 10, and for shell 2, this happens as a constant kinetic rate of rate 1. And this will be later on, when we get the flux vector, we will get a constraint, because the reaction, let's say R1 here, R2 here. So we get that this flux vector V1, V2, so the process vector will be such that V2 is generally smaller than 10 times V1. Sorry, 10 times V2 is smaller than V1. So because there is a rate, a kinetic rate, and if we assume that both shells have nearly reasonably similar populations, then we have to constrain the region of the process space to this shape. So the angle of the process vector, it's already around a certain area. And then we can describe how the dynamics will unfold in these conditions.
Perfect.
So there are many ways to introduce mathematically the type of conditions you mentioned.
Okay, so this is great from the ecological point of view and for the application. So then I'm curious about, now if you have to talk to a mathematician, what type of theory you're developing for this?
What type of theory?
Mathematical theory. If you need to sell this to mathematician that you're developing new math, what type of math this is?
There are many ways to that. There is a part I didn't show because of time, but the idea of the okay. There are two things I would like to say. The first, it's an abstract form of dynamical systems. So we are looking at dynamical system of subspaces instead of dynamical systems of points, or like attractors seen as regions of a phase space. And now we are looking, instead of points, we're looking at the subspaces. So that will be a sort of, we can call it spectral theory, spectral dynamical system, structure and spectra, or something like that. And the other, which is the most interesting to me, is the constructive, the order theoretical analysis we do when we look at these substructures that have a hierarchy, what follows what. And then the theory of resilience that we are developing, that is based on this Markov graph, where more resilient graphs are visited more often. That's also something like new mathematics, but yeah, it will depend on which mathematician. If it's an analyst and a topologist, or an algebraist, I will have to sell it differently, actually. Yeah.
Okay, perfect. These are not innocent questions I'm asking. I'm biting, like there is something behind this. So it's great. Like, yeah, I have two hats, and the students in the room, right now they're all mathematicians. so like the ecologists don't know where they are. Sophia is there, right? So I'm asking this because to have, like, always, it's good to have something mathematically in, at least for some of the dissertations of the group. Some of them, if they don't care about following a faculty position in a math department, doesn't matter. Just being a scientist is great. But some of them might want to have something more, like, to show us mathematical. So this is great for that. And I'm looking at the person that I know is interested. So yeah, it's good to know, and we will follow up on that.
Yeah, I will have to get a little bit of the background or interests, because there are relations with dynamical systems, but there are also relations with computational complexity theory, which I don't know if mathematicians there work in computational complexity or just have to go to the computer science department. There are also relations with representation theories in logic, in this with mathematical logic. Actually, there is a lot of mathematical logic behind, which is not, I couldn't explain, but the sets of closed sets for the mathematician in the audience, the set of closed sets can be equipped with logical operators like joint, which means joining the things, or union, like joint, and meet, which is the sort of generalization of intersection. And you can create a structure called lattice, which I don't know if the mathematicians there are familiar with, but it's a sort of proto-logic. We can define negation operators as well, orthogonality operators, and then it turns out that the set of organizations is actually, as for certain kinds of reaction networks, it has the properties of a logic which can be Boolean in some cases, but in some cases it's not Boolean. I made an article in the journal Foundations of Science where I show a sort of ecological system, a very weird ecological system, whose lattice of organizations is not Boolean, meaning that meaning that there are synergies, basically. The non-Boolean structure, it means that 1 + 1 is 3 or 1. So you cannot think of that. That's the corollary from the mathematical perspective, that we cannot think of climate change as something very rational. There are things that don't add up in the way if we look just simply at it, they will not add up as we will expect. So there is some sort of irrational, how to say, events, like probabilities will not, Kolmogorovian probability theory will not necessarily be the best way to look at what is more likely to happen. So this, it's complicated to explain, but it's in the article if the mathematician want to take a look.
Yeah, so that's all great. So we will take a look, we will see the level of interest, and knowing the type of names, the type of theories will allow us to find QE members. Or like qualification exam members for the interested person.
Okay, yeah, cool.
Yeah, no, I have a reason for all these questions.
Okay, yeah, I will be glad to know more if needed.
Yeah.
So can we set up maybe another meeting with whoever is interested to think more deeply about these mechanisms that you were mentioning? Because this is the sort of problem we have, is that we got the theory, we got the intuition, but we don't know the real problems. And I've been trying to get closer to ecologists, but it just takes me quite some time to even explain the framework, the ideas, the theory. So I've been like, I have it's not easy to find a group of ecologists that can be open to think of this for an hour, and a half, and then not be.
We've been hours, 1.5 and 1.5.
Yeah, well, that's great. So yeah, I will be really glad to follow up on this now that you have a little bit of the intuition, and apologize for not having a better way to present this. It's really, I haven't found a way to explain this in a more pedagogical way, despite the lots of articles that I've written about. So I still haven't written the right article for ecologists to explain this. So maybe you will help me with that. You might be a lot of help.
Yeah. No, this is what complexity sciences is about, like understanding each other. Yeah, no, I think that was a great presentation. I followed all what you showed, and I think that everyone here is kind of nodding, so we're all good. Although everyone in the room, except for me, are mathematicians. Okay, so thank you very much, Tomas. I will follow up after I have conversations here. Of course, regardless, we can follow up anyway, the two of us. And yes, this is great. Thank you very much.
Okay, thanks to you. I'll stop recording then.